You'll notice is that everything will be handwritten. I'll do my best to try to make it legible. But all of this should be video recorded too, and I don't promise that it will work perfectly, but I'll try to make it work pretty well throughout the term. So the first thing we're going to be covering this term is the introduction to addition reactions. And addition reactions will look really familiar to those of you that remember Chapter 8, because it's essentially the reverse of elimination reactions. So let's first cover our elimination reactions, and then we can contrast and compare them. So the example we did in lab was we started with cyclohexanol, and we heated it up, and what did we need to add in order to drive the elimination reaction? Yeah, we needed to add some sort of acid, so I'll call this H+, and I'll put it in brackets because we know it's a catalytic amount of acid. It's regenerated during the reaction. And when we do this, we can actually drive off water and form our new alkene, right? So is this an E1 or an E2 reaction? E1. So when we use the acid, we're going to protonate that alcohol. It's going to pop off on its own, and then we can have water act as our base. So you may want to review some of those elimination reactions if you're a little rusty with them. But the thing that's important to remember for these elimination reactions is that they result in a new double bond. So elimination reactions result in a new double bond. How can we favor elimination reactions? We already touched on it. High temperature. So the reaction is favored at high temp. The weird thing is when we compare this to an addition reaction, they look really, really similar. So addition reaction. So let's take an alkene, like cyclohexene. We'll add water. We'll add acid. And all of a sudden we've done the same reaction, but in the reverse direction, right? So the question is, why are we able to do this reaction going one direction one way and the other direction the other way? And how are these the same, or how are they different? So let's take a look at this in a little bit more detail. So in this example, this may sound a little redundant, but instead of going from a single bond to a double bond, we're actually going from a double bond to a single bond. And the reaction is favored at lower temps. And we'll talk more about this reaction and the mechanism behind this a little later. The interesting thing with these addition reactions is the thermodynamic parameters for it. So if we look at this, is this becoming more organized or more disorganized? More disorganized, right? Or more organized, excuse me. We're taking 2 moles of starting material going to 1 mole of product, right? So if we're looking at the delta S value for this reaction, is it going to be positive or negative? Negative, right? So if we're creating more disorder, it would be positive, but in this case we're creating more order, so it's actually going to be negative. And if we go through and we look at our bond dissociation energy table and we actually calculate delta H for this reaction, we would see that delta H is also negative. So we're in kind of a unique boat where we've got both delta S and delta H negative. So if you remember back, I can't remember which chapter it was. This is a chapter on thermodynamics we had one really important reaction. We said that delta G, that Gibbs free energy, is equal to delta H plus negative T delta S. You guys remember that? So Gibbs free energy is the term we use to predict whether or not a reaction will occur or not occur in this case. So if we look at delta H for this reaction, we know that delta H is negative. So we've got a negative plus this whole term right here. Will that be negative or positive? It'll be positive, right? Because the two negatives will cancel out. So we've got a negative term, that delta H, the enthalpy, and then our entropic term will actually be positive. So we know in this case we've got delta G equals a negative plus a positive. This gets a little bit confusing, and we had a problem of the day where we actually addressed this last term. So if we're running this reaction at high temperatures, this term will dominate, right? So at high temp, the entropy term dominates. Right? Because if we increase that T value, that number will become more and more positive. Right? But at low temperatures, will that entropy term dominate? If we run T close to 0, that term is going to become smaller and smaller. And then our enthalpy term will become the dominant factor. So at low temp, enthalpy term dominates. So if we run this reaction at high temperature, will delta G be positive or negative at high temperatures?
Positive.
Yeah. So let me fix this. At high temp, delta G is positive, which means that the reaction favors our starting material, right? So if delta G is positive, that reaction probably not going to go. It may be at equilibrium to some degree, but it's not going to favor the product side. It's going to favor the starting material side of the reaction. At low temp, delta G is negative, and the reaction favors product. So if we go back and we look at this reaction, if we're trying to favor formation of the product, we need to run this reaction at a low temperature if we want the addition reaction to occur. If we want to go from cyclohexanol and go back to the starting material side, we need to run it at a high temperature. So the reality is that this reaction is more or less in equilibrium, and we can favor that equilibrium by adjusting the temperatures for this reaction. So again, we're kind of relating this back to the thermodynamics that we covered last term. Does that make sense? All right. So let's continue on and actually cover a new type of reaction, and these are called hydrohalogenation reactions. Hydrohalogenation reactions are pretty neat, they're pretty intuitive, and they work well. So the first thing we need is we need a double bond to react. So I'm just going to start with this allyl group. So we've got a single bond and a double bond. And this time we're going to react it with an acid. And I'm going to just pick hydrobromic acid. The reality is you can pick any halogen-based acid that you want, so hydrochloric, hydrobromic, hydroiodic acid. It works with all of them. The cool thing with this is that we've got a nucleophile. Which one's our nucleophile, the double bond or the hydrobromic acid? The double bond. Why is it a nucleophile? Yeah, it's got those p orbitals that have electrons in them. So in this case, our double bond is going to be our nucleophile. And if we look at hydrobromic acid, we know that the bromine is electronegative, so it's going to pull electron density away from that hydrogen, which makes it a very good electrophile, right? And actually, I'm going to change the color of our hydrobromic acid here really quick. That way we can emphasize where the different bonds are being made and broken. All right, so this double bond can come in, attack our electrophile, and are we done? No, we've got to kick off that bromine, or else we're going to have a positively charged hydrogen, and that would look pretty ridiculous. So if we do this, we've got a couple different options of products. We could have the hydrogen add here, or we can have the hydrogen add over there, right? So we could have it add to either side of that double bond. Which one do you think is more likely, the left carbocation or the right carbocation? So I hear some people saying left, I hear some people saying right. Which is the more stable carbocation? The right one, right? So if we look at this one, we've got a primary carbocation. This one's secondary. We know secondary carbocations are much, much more stable. So when you do this reaction, you're never going to form the primary carbocation. You're actually only going to form your secondary carbocation just simply because it's much, much more stable. All right, so we've also got some of our bromine floating around, or bromide, excuse me. So we've got this Br minus floating around. This Br minus is going to be a nucleophile or electrophile? Nucleophile, right? And our cation will be our electrophile. So that bromide can attack from either the top face of that carbocation, or it can attack from the bottom face, right? So if you remember, our p orbitals for carbocations can stick either up or down. So this bromide can attack from either face. So if we look at the product of this reaction, we've got one where this bromine is adding from the top. And let me fill this in here. And we've got another one where it's adding from the bottom face. Let me draw in our hydrogens that we know are on there. Are these the same or are they different? They're the same, right? Because we've got two methyl groups on there, so we can draw both enantiomers of this, but both enantiomers are the exact same product. So we don't really need to worry about stereochemistry in this case. So this is all it really is for hydrohalogenation. The cool thing about this is if you look at the double bond, the bromine adds to the more substituted side and the hydrogen adds to the less substituted side of the double bond. And this reaction was very popular. It was studied a lot in the 1800s, and the Russians in particular studied these reactions quite a bit. Specifically, it was named after Vladimir Markovnikov. I think it was like 1869 when he was studying this. And so these reactions actually got named after him, and they're called Markovnikov addition reactions. And what that means is that the halogen adds to the more substituted side of the alkene. And these are called Markovnikov addition reactions. The thing to remember is that you have to watch out for stereochemistry with these reactions, because that halide, when it's acting as a nucleophile, can attack from either face of the carbocation. I'll say watch out for stereoisomers. So this reaction isn't stereospecific, right? Because we know that it can form a mixture of enantiomers. but is it regiospecific? What do you guys think?
No.
It is. So in this case, the bromine can only attack at this position on our double bond, so that makes it regioselective but not stereoselective for this reaction. So that was a term we briefly mentioned a little bit last term. So it's important to remember that this reaction is regioselective.
That's because that bromine can only attack.
It can only attack that carbon 2. It will never attack carbon 1.
And if it could, it would be
If it favored only one enantiomer over the other, so for example, if it only could approach from one top face, then it would be stereospecific or stereoselective. Yeah.
So is it both regio and stereoselective?
So in this case, it would just be regioselective. It wouldn't be regiospecific or sorry, it wouldn't be stereospecific or stereoselective. It would just be regioselective. Yep. All right. So let's talk a little bit more about this reaction. And we'll do this by looking at an example, because this reaction just takes a lot of practice. Most of it's fairly intuitive, though, so hopefully it isn't too much of a challenge for you guys. But let's start with this alkene. And again, I'm going to use HBr. Oh. What will the first step be? Yeah, protonate the pi bond, or that pi bond will grab that proton, however you want to describe it. We know that there's a dipole, so that alkene will come over, grab that proton, kick off our bromine, and then we've got to look at our product. Are we going to form the cation there? Oop, let me erase that. Or are we going to form the cation there? Which one's more stable, the one on the left or the right? The right. So if we look at this, we could have the hydrogen add to either side of that double bond. However, our product's going to be a lot more stable if we go to our product on the right. So in this case, we know that this product won't be observed, but we will have the tertiary carbocation, which is much, much more stable. And we've also got this bromide floating around. So if this bromide floats around, it wants to find a positive partner to bond with. This one can attack from either that top face or the bottom face of that carbocation, with equal probability in this case. And so if we look at our products, we may want to look at our stereochemistry. So for one of these, we'll have a methyl group sticking out and the bromine underneath. And for the other, we will have our bromine attacking from that top face and our methyl group sticking down. Yep?
I remember from last year that there was the Hoffman product and the Texas product, and that different reactions made it so that it's more favored, and you pick one over the other. So like this for the first part, we crossed out one.
It's similar. So a lot of times what we have to do is we have to look at the relative stability of the transition state. So for the transition state going to the secondary carbocation, that's a lot less stable than the transition state going to the tertiary carbocation, which means this reaction pathway is going to be much more favorable. It's going to have a lower activation energy. It's a little different. We don't use the term Hoffman or Zaitsev for addition reactions. We only use those for elimination. That's a good question, though.
So is there one thing that's going to do with the product?
Where it goes to the secondary carbocation?
Yeah.
Not really. We'll cover more of those reactions later. What usually happens if we have an unstable carbocation? Yeah, some sort of rearrangement. So we'll cover that here in a bit, though. But if we look at the set of products that we've got here, what's the relationship between these two products? Sorry. We don't really use cis and trans when we're looking at pairs, right? So if we're looking at these as a pair, are they diastereomers, enantiomers? They're enantiomers. So in this case, we get pair of enantiomers. So in this case, we're not favoring one stereoisomer over the other. However, we are only getting one regioisomer, meaning that bromine still is only attaching to one position. It won't attach at the other. So in this case, this would still be regio-selective. But we do get a pair of enantiomers, and oftentimes this is going to be equal mixture, very close to an equal mixture, depending on any other stereochemistry going on within that molecule. All right, so there were some strange observations when they were studying this reaction. The first one was that in the 1860s, buying reliable chemicals wasn't an easy thing, right? So they would do this reaction, and they'd say, all right, I'm going to get some hydrobromic acid. It should result in this product. But oftentimes what they would observe was they would add hydrobromic acid, and instead of getting that top product, they would actually get the bromine adding on to the other side. And for quite a while, this was a challenge. Nobody could figure out what was going on or why it was going on. And then they realized that their chemicals that they were using, the hydrobromic acid, was very impure, or even a little bit impure. And the impurity was causing this reaction to proceed differently. So I'm going to abbreviate this ROOR. So ROOR equals a peroxide. So there was some sort of peroxide product or byproduct in their hydrobromic acid that actually changed this reaction so that the bromine added to the other side. So in this top reaction, we observed a Markovnikov addition. In the bottom reaction, if you inadvertently or purposely add peroxides to this reaction, you can actually get the bromine to add in the opposite position. So this is called anti-Markovnikov. And all anti-Markovnikov addition means is that the bromine in this case actually adds to the less substituted side of that double bond. There were some weird things that they discovered about this, and we'll talk about this more in chapter 11. So I don't expect you guys to know the mechanism right now, but in chapter 11, we'll talk more about this mechanism, because it is a really unique mechanism, and it only works with HBr. It doesn't work with hydrochloric acid or hydroiodic acid. It only works with hydrobromic acid. Yeah, Kareem?
When we're doing these reactions, the fact that we're making products, would you tell us if it was impure or pure?
Yeah, I would say peroxides or no peroxides.
Okay.
So in this top example, you'll notice there's an absence of anything underneath the arrow. So if I don't have anything written there, you should assume the hydrobromic acid is completely pure. If I write peroxides underneath the arrow, you should instantly think anti-Markovnikov. That's a good question, though. All right, the other thing that we talked about briefly already was carbocation rearrangements. Because we know anytime we form a carbocation, there tends to be this possibility that things will rearrange to form a more stable carbocation. So let's take an example here. So we've got our alkene. This time I'm not going to have it be with peroxides. We're just going to do our traditional addition reaction. The first step we said will be the double bond attacking this hydrobromic acid. We'll kick off bromine. We know that the hydrogen is going to add to the more substituted side or the less substituted side of the double bond? Less substituted, right? So in this case, we know that we're going to be forming a carbocation in this position. Are we done yet? What can we do? yeah, we can do a methyl shift, right? So in this case, we've got a methyl group nearby. So this methyl group can actually hop over. And if we do this, we get a 1,2 methyl shift. And our new rearranged product is significantly more stable, right? So if we look at the one on the left, we've got a secondary carbocation. If we look at the one on the right, we've now got a tertiary carbocation, which is much, much more favorable. So this occurs spontaneously and is very hard to control. So the next step, we'll have our bromine add in, and the reality is that this rearrangement sometimes doesn't completely occur, so you can get a little bit of bromine reacting with the secondary carbocation. It's not a perfect reaction. So if we do this, this can attack from there or there. When we do this, we can draw it out. So that bromine can add from that top face, or it can add from that, or it can add from that bottom face, because we know that that p orbital has very equal probability, or it can add in to the tertiary carbocation, which are going to be our major products probably. The product on the right or the products on the left? Probably on the right, because we're going through a tertiary carbocation that's more stable. So in this case, we can box these off, and we can say this is going to be our major product. This will be our minor product. So the reality is, anytime you run these reactions, you're going to get a mixture. It's very, very hard to control that. Yep?
With a polar solvent, can you favor the minor product?
Not easily. It can be very challenging. You normally get a mixture, regardless. There are some weird situations where you can get that, but we're not going to go into detail on that.
So like I said earlier, because the bromine can flip into places, that makes it not regioselective, right?
So addition reactions are usually regioselective, but not usually stereoselective.
So this would still be regioselective?
Yep, because that bromine will only add to one face. Or sorry, let me rephrase that. This would be, yes, this would be regioselective because we're still forming a major product, so one regioisomer is favored over the other. We're not going to get too into semantics on what we're calling this, but I do want you guys to understand the mechanisms for these. That's the most important part for this chapter. Yep?
That's stereoselective.
So if it's stereoselective, we're comparing a mixture of enantiomers. And in this case, this enantiomer isn't favored any more than that one, so this one wouldn't be stereoselective. Sorry, I keep on flipping it too. The key take-home message from this is it results in a mixture of products. And essentially, it's hard to control. Rearrangements occur even if you don't want them to, and sometimes they occur when you don't want them to. It's a mess trying to plan a rearrangement into a synthesis problem. All right, so I think we've got enough time to start on to a little bit of a new reaction, but it's very, very similar, so it won't be anything too earth-shattering for you guys. These are called acid-catalyzed hydration reactions. So with acid-catalyzed hydration, it's very, very similar. The overall reaction is you've got an alkene, some water, some sort of catalytic amount of acid, and you'll get an alcohol installed in a more substituted position. So it's very, very similar. but let's break down the mechanism for this reaction piece by piece. So the first step is we've got water in the presence of a strong acid. What do you think is going to happen with that? You're going to protonate the water, right? So acid-base reactions are always going to be the quickest reactions in organic chemistry. So the first step is we've got water, we've got some H plus around. We know that this will very easily form hydronium ions. So if we want to be thorough and draw the reaction arrows, we're going to do that. All right, the second step is that we now have hydronium and our alkene. So we've got our alkene here, and I'm going to draw the hydronium as, let me actually change it to blue so we can see again where the various pieces are going. It's just like with our acid, whether it's hydrobromic acid or hydronium, this double bond will come and attack the hydronium, kick off water. We know in this case the hydrogen is going to add to the less substituted side, so we have the more stable carbocation. So in this case we've got our hydrogen over there. And we've also kicked off water, so water is going to play a very important role in this reaction. Got plus OH2. Let me erase that. This water can act as a nucleophile and add into either the top face or the bottom face of that carbocation. Both are equally likely. And when you do this, are we going to get a mixture of products, or will the mixture just be the same? Be the same. So we could draw both enantiomers, but both enantiomers are the same molecule, so we don't really have to worry about stereochemistry. So now we've got OH. Whoop. Let me stick with the color scheme I had. Got OH2 plus, and we've got our hydrogen over there. And we're not done yet. We've got our third step. Exactly. So water isn't very happy when it's protonated, or an alcohol is not very happy when it's protonated. So in this case, we've got this situation here where we need to do one last deprotonation. This reaction, like we said, is normally done with water. So water can act as a weak base. So we've got water over here. This water will reach over, grab one of these protons, and become our new catalytic acid. Let me finish using my black marker here. So we've got OH and H. So the cool thing that we saw with this is that we regenerate our catalyst. All right. The neat thing with this reaction is you can use any alcohol. You don't have to use water. Water is just the most ubiquitous alcohol. So oftentimes this is just called hydration, but you can use methanol, ethanol, any sort of alcohol and still get this reaction to work. And we'll start class tomorrow going over some examples of these reactions. But one thing to notice on the problem of the day is that you may need to think a little bit more in depth about stereochemistry, and again, this is a good one to break out the model fits for. So if you do struggle with this, maybe try building the model of the reaction mechanism and see if that helps you out with it. Remember that Monday lab, we are meeting today, so we're going to meet upstairs here in a few minutes.